Okay, today let's talk about homotopic version of Cauchy theorem and simple connectivity. Okay, so we are considering the following property. So first of all, you see we have certain curve. You can consider it as a rubber band, and you can stretch it and can shrink it. Assume its original position is a stretched position, then you can. Once you release your force, then it will be shrinked to the stable condition. So basically, this curve, the large curve, can be shrinked to the smaller curve. And we want to study the property of this shrinking process. So that's our first definition. Okay. Let gamma 0, gamma 1, both from 0, 1 to G, be a two closed rectifiable curves in a region G. Then gamma 0 is homotopic to gamma 1 in G if there is a continuous function capital gamma from 0, 1 cross 0, 1 to G such that the gamma S0 is gamma 0 of S, and capital gamma S1 is gamma 1 of S for S between 0 and 1. And second condition, gamma 0 of T is equal to gamma 1 of T for T is between 0 and 1. Okay, so what is this capital gamma? The capital gamma is a following function. So we go through this process, we see that between these two curves, or between those two status, there are several possible positions for this rubber band. Okay, so for each position, let's assume this is gamma 0 and the final position is gamma 1. For each middle step, you can consider it is parameterized by the parameter t, gamma of t. So assume this is the initial and terminal point. This is the initial and terminal point. And then each middle step is also a closed curve. It has initial and terminal point. So the second condition just means for each middle step, gamma t, it is a closed curve. Initial point is equal to the terminal point. And gamma S0 means the first curve is gamma 0. And gamma S1 means the final curve is gamma 1. And this t is a parameter among curves. S is a parameter for one curve. Okay, so S is a parameter for one curve, but T is a parameter between curves. Curve 1, curve 1/2, curve 1.1, curve 1.2, something like that. Okay, so that's the idea. And if gamma 0 is homotopic to gamma 1, we write gamma 0 is like this, with this symbol, tilde. Gamma 0, tilde gamma 1. They are homotopic. And we can show that this tilde is an equivalence relation. Okay, so what is an equivalence relation? A relation is equivalence. A relation is an equivalent relation if first an element, the element in the consideration, an element is equivalent to itself. Second, x is equivalent to y, then y is equivalent to x. And third, transitivity, x is equivalent to y, y is equivalent to z, then x is equivalent to z. Okay, so an equivalence relation is characterized by those three properties. And now for the homotopic equivalence relation, we can easily see gamma is equivalent to gamma. We can just define capital gamma of ST as a gamma S. Okay, so this is a equivalence relation. This is the capital gamma in the definition. So it implies gamma is equivalent to gamma. It's homotopic to gamma. And second, gamma 0 is equivalent to gamma 1. It means you have a capital gamma ST, and then we define capital prime of ST to be gamma S 1 minus T. Gamma S 1 minus T. Then we can see that the gamma prime is the function in the definition of gamma 1 is a homotopic to gamma 0. Okay, so you just verify those two properties. Okay, and 3, the transitivity. If gamma 0 is equivalent to gamma 1, then it is equivalent to that there exists a capital gamma 1. Let's put gamma 1. And gamma 1 is equivalent to gamma 2, is homotopic to gamma 2. It means there exists a gamma 2, capital gamma 2. Then we define capital gamma 3 of ST to be capital gamma 1 S 2T if T is between 0 and 1/2, and capital gamma 2 of S 2T minus 1 if T is between 1/2 and 1. Okay, so by this capital gamma 3, we can verify that by capital gamma 3, gamma 0 is equivalent to gamma 2. Okay, so this is the verification of the statement. The homotopy is an equivalence relation. Very fast, very fast. If you don't follow it, just go over it by yourself. You will see it's not a tricky problem. Okay. Uh, Now let's see. Not every pair of curves are homotopic to each other, or not every curve is homotopic to a point, but there is some special domain which have some nice properties. First special domain is a convex set. A set G is convex if given any 2 points A and B in G, the line segment joining A and B, we write like the interval AB. It's a line segment joining A and B, lies entirely in G. Okay, so arbitrary pair. You draw this line segment, it's inside G. And the set G is star-shaped if there is a point A in G such that for each C in G, the line segment AZ lies entirely in G. Okay, and we say that G is A star shaped. This A is this number A, letter A. Okay, so for the star-shaped region, we will imagine the star, the star. Oh, sorry, my bad. What should I draw it? Okay, sorry. Yeah, this one. This is the one I want. The star. This is a star-shaped region. So you can pick up a point A here, then any Z here, you can connect A and Z, and this segment is entirely inside this star. And this A sometimes it's not unique, so you can choose A here, you can choose A, you slightly move the A, this A also works. And sometimes you can randomly pick up A. For example, if you have a circle here, whatever point A will play the role as this A star shaped. And sometimes this A is unique. For example, you just pick up a cross. You pick up a cross, A can only be this point. Here we only say a set G. We don't mention G is always open, so this is allowed. This is allowed. Okay, it doesn't matter. We just need one such A. That's enough. Okay. Star-shaped region or star-shaped set is always connected because you can always connect 2 points by connecting them to A. So each star-shaped set is always connected. So that's not the weird conclusion. Okay, now let's see the proposition. The proposition is the following: 6,4. Let G be an open set which is A star shaped. Okay, so we emphasize this G with a special choice A. And if gamma 0 is a curve which is constantly equal to A, then every closed rectifiable curve in G is homotopic to gamma 0. Gamma 0 is a constant curve. Okay, so all the rectifiable curve, closed rectifiable curve will be homotopic to a constant curve. And if it is a star-shaped. By the way, we know that the convex set is a star-shaped set. Every point A inside the convex set can be the choice of A. Okay, so the proof is very simple. The proof is that let gamma 1 be a closed rectifiable curve in G, and define gamma st to be gamma 1s. So okay, let's just use a convex set to demonstrate the G. A is here. Gamma 1, this is gamma 1. Gamma 1s, this is gamma 1s. Then we are going to connect this gamma 1s to A. This whole segment is inside the G by the definition of A star shaped. And the segment, well, the segment, it depends on how do you say the initial and terminal point. And we assume this the constant point A, the A is a constant curve gamma 0. So we start from A and we go to gamma 1s, gamma 1s. So when t is equal to 0, it is equal to A. When t is equal to 1, it is equal to gamma s. Okay, t is equal to 0, it is equal to A, so t is with gamma 1s. Okay, so gamma is from 0, 1 cross 0, 1 to G, and gamma is continuous. Hence, gamma 1 is homotopic to gamma 0. Okay, just use the straight segment to connect the point to the fixed point A. Okay, we are going to use this homotopic condition a lot, and also we will use this homotopic condition to the constant curve a lot. So that's the reason we have the following definition, because we will repeatedly use this concept. If gamma is a closed rectifiable curve in G, then gamma is homotopic to 0. We write gamma is homotopic to 0. if gamma is homotopic to a constant curve. Gamma is homotopic to a constant curve. Then we say it is a homotopic to 0. Okay. Okay. The Cauchy theorem, the second version of the Cauchy theorem. Well, what is the first version? First version means if you have a closed rectificable curve, so that the Wanning number with respect to the exterior point, not exterior point, the point outside of the set is always 0. The Wanning number, if the Wanning number of the curve with respect to the outside point is always 0, then the analytic function integrate over this closed curve is always 0. So that's a Cauchy version, a Cauchy theorem first version. Then now the Cauchy theorem and second version. Is that if f from G to C is an analytic function, and gamma is a closed rectifiable curve in G such that gamma is homotopic to 0, then the integral of f along gamma is equal to 0. Okay, so this is the second version of a Cauchy theorem. Whenever you can shrink, basically we will say that whenever you can shrink this curve to a point, then the integral is always 0. Okay. Okay, so this is a second version of Cauchy's theorem. In the very straightforward idea, we can see the following proof. So how do we prove it? We have gamma, and it is homotopic to 0. Let's assume this point is inside. Homotopic to 0 means it's homotopic to a constant curve. Homotopic to that constant curve, that constant point may be inside, outside, or even on the curve. It doesn't matter which point it is. Assume you can do that. Let's assume this is a homotopy between the gamma, the capital gamma between them. We are going to do what? This is a, let's say this is a gamma of S0. This is a gamma of ST, the little gamma TS. Okay, so we may define h of t to be the integral of f along gamma t, and we show that h of t is constant, and h of 1, h of 1, this is point A, let's choose A. H of 1 is the integral of f. Here is gamma S0, this is gamma S1, the curve, and it is integral over the point. The integral over the point is 0. So h of 0 is gamma is equal to 0. So that's a very straightforward idea. So how to prove that this is the integral is 0. And actually this is the original idea. Why do we want to shrink it? We want to change from one curve to another curve so that we get the same integral for the analytic function. Okay, but there's a serious problem. The serious problem is that when we get this gamma st, we say it is continuous, but for each t between 0 and 1, for fixed t, gamma st may not be rectifiable. At least we don't know if this gamma st is rectifiable or not. So we cannot even define the integral of f over the middle step gamma t. So that's the problem. Okay, so we cannot just use these stuffs. We have to modify it. Oh, of course, this is the right idea, but we have to modify the step. And also, we don't just prove this Cauchy theorem for the homotopic to zero curves. We are going to prove an even more general version of a Cauchy theorem. This is called a third version. Third version says if gamma 0 and gamma 1 are two closed rectifiable curves in G, and gamma 0 is homotopic to gamma 1, then the integral of f along gamma 0 is equal to the integral of f along gamma 1 for every analytic function. F in G. Okay, so this is a more general version of a Cauchy theorem compared with the second version. Because if gamma 1 is a constant curve, then this is still the 0. Okay. Okay, so we are going to prove this, and the second version of a Cauchy theorem will be a corollary. There are two proofs. The first proof is a special case. Okay, so we want to put some strong condition. Assume or suppose that capital gamma has continuous second partial derivative. Okay, so if it has continuous second partial derivatives, the mixed partial derivatives does not depend on the order. The second partial derivative, the mixed second partial derivative has mixed term. The mixed term normally has partial s partial t and partial t partial s. If you have continuous second partial derivatives, these two things are equal. Okay, and then let's see. We are going let gamma t s to be gamma st. So the middle step, gamma ts is gamma st, capital gamma st. Then we define this g of t as integral of f z dz along gamma t. The same thing. That part we use h, here we use g. It's a smooth curve. It is differentiable. So it's from 0 to 1 f capital gamma st and partial gamma partial s st ds. Okay, remember this is a fixed t it is a middle step curve. Okay, and if we get 0, it's the integral along gamma 0. If we get 1, it's an integral along gamma 1. So we're going to show that G is a constant. We need to show G is a constant. How do we show G is a constant? We do the differentiation. So G prime of T the integral is about S. This differentiation is about T, and apply the Leibniz rule we have. We can interchange the integration and the differentiation. And then we apply the differentiation to the F and the partial capital gamma partial S. You have a product, so you apply the product rule. Sorry, not F. Okay. So exchange the integration and the differentiation, that's Leibniz rule. And inside this differentiation is a product and the chain rule. And then this part, we're going to use the property that partial S, partial T, partial T, partial S are the same thing. And I also exchange this. No, I keep. Yeah, I keep this so far. Okay, now let's see. We put these two together. These two together, we get the derivative of DDS F gamma ST. We use D, we'll use partial, same thing. And then times partial T, partial gamma partial T. And this part, we get F gamma ST partial S partial gamma partial T. It's the same product rule, but for the different variable. Okay. And then this is the product rule. And this is the product. Okay. So just try to differentiate this and compare these two derivatives. And the differentiation integration, they are inverse to each other, so you get F gamma. It's about S, so this is antiderivative. 1 T gamma minus F gamma 0 T gamma T. Okay? And this is a closed rectifiable curve. So these two things are equal. So what we have? We have 0. We have 0 because this is the closed rectifiable curve. Well, so far this is a correct, complete answer, complete proof, but with a very strong condition. Gamma has continuous second partial derivative. We even don't know if gamma is closed rectifiable or not. But here, we could finish the proof if we have such a condition. Now let's see how do we get the general proof. So we only prove the special case. We don't have the proof of the general case. Okay, so let's see the proof. Let's get capital gamma from square to G. Satisfy the condition in the definition of gamma 0 homotopy to gamma 1. Okay, it satisfy those two conditions. And the square 0, 1 cross 0, 1 is compact, closed rectifiable. Gamma is continuous, then capital gamma is uniformly continuous. Okay, uniformly continuous, and the gamma of I square is a compact set of G. So the continuous image of a compact set is compact, so we use this property. Continuous image of a compact set is compact. And because this image is compact, then the distance between the image and the boundary of G is going to be strictly positive because it is totally inside the G. So the distance will be strictly positive. Strictly positive, then we are going to use small neighborhood to draw the disks. Then there is an integer n such that if s minus s prime square plus t minus t prime square less than 2 over n squared, the distance is small enough, then gamma st minus gamma s prime t prime, the distance is less than r. So basically this is uniform continuity, and also plus they are off the boundary. Okay, so these 2 points should be very close, and this distance is less than, this distance is small, and here it should be less than r. It's less than r, less than r. So you draw the disks. Draw the disk. This point is inside the r. Inside disk with the radius less than r. Okay. Okay. So what do we do? So assume the gamma of I square. So gamma 0, 0, gamma 1, 0, gamma 1, gamma 1, 0, yes, gamma 0, 1, gamma 1, 1. Assume this is the images of them. And then what we do, we're going to put some lattice here. We just choose this point, this point, this point, this point. Like the sample point, the pixels. Okay, so we got those pixels. We let zjk be gamma of j over n and k over n, and jk both between 0 and n. So basically, z, j, k are those pixels. The image, they are in the image set. And let capital J, j, k to be the j over n, j plus 1 over n cross k over n, k plus 1 over n. They are in the domain, the small square. The small square, we will have the z, j, k, z, j plus 1k, z, j, no, this is a z, j plus 1k, z, j, k, this k, so j is, it's k plus 1, yes, z, j plus 1k. Okay, for the same level, this is a j's, j plus 1s, j plus 1s. And here I have a k plus 1. Vertical and horizontal. Okay, so that's the setting. And the diameter of jk is root 2 over n. So the diameter is root 2 over n. Smaller than, remember here, 2n over n squared. Less than 2 over n. Then you have gamma jk totally inside the open disk centered at zjk with a radius r. So this is the image, and the radius is r. You use this point as the center, and you have radius. Okay. See, let P, J, K be the closed polygon. ZJK, ZJ plus 1K, ZJ plus 1, K plus 1, and last one, ZJK plus 1, and ZJK. What is this? The polygon like this. You go this way. It's not the curve, it's a straight segment. You go this way, you go this way. We just pick up the pixel, so we choose a straight segment and go to the previous point and back. So it's you can imagine that it's a counterclockwise, but in the plane it may not be counterclockwise. We just imagine with this setting it's counterclockwise. Okay, so it's a region with 4 sides, straight segment polygon. Okay, and those points are inside open disk, and the disk is a convex set. This polygon PJK is also totally contained in the disk centered at the ZJK with radius r. So it's totally inside this big one. Okay, and since it's inside this closed disk, then we know the integral of f along PJK. F is analytic, so every closed rectifiable curve gamma and analytic function f, the integral of f along gamma is always 0. Okay, we already proved that because there is an antiderivative. Okay, now we are going to do what? You see here, we have a gamma 0. have gamma 1. From gamma 0, we get okay, assume this is a P, okay, the case level, the first level, KJ, P1, P10, P20, P30, P40, P50, P60, P70, and P80. Okay, so that's the first ground level. And you have the upper level, k equal to 1. So you have this P11, P P21, P31, P41, and P71. Okay, so what we do, we are going to first, we replace this gamma 0 by this, not P, this is J, Z, I'm sorry, this is Z. All the points are Z. All the points are Z. It's not P. P is a polygonal curve. All the points are Z. So first, we don't want to use the closed rectifiable curve gamma 0. We want to use a polygonal path from Z0 to Z1, Z10, Z20, Z30. We use this polygonal path to replace this gamma 0. And then we are going to lift this polygonal path up and up and up, step by step. Eventually we reach the top level. Okay, so that's the idea. So first we show that the integral of f along gamma 0 is equal to the integral of f along what? Z10, Z20, Z30, Zn0, Z10. F. This is the polygonal path. It follows the same order of gamma 0. Okay, same direction orientation. How do we show that? We just get it for one thing. So from this is a gamma J0, Z, not a gamma, Zj plus 1, 0. This is a one arc and a one sector. This is arc, it's a sector. The closed curve arc Zj0, Zj plus 1, 0, union the sector, the segment, not the sector, the segment Zj1, J plus 1, 0, Zj0. So you go forward and backward. This is a closed rectifiable curve. The arc is a part of a rectifiable curve, so it is rectifiable. And this segment is rectifiable, so the union is rectifiable. It starts from Zj0 and back to Zj0, so it's closed. For this closed rectifiable curve, it is in the open disk centered at whatever point you want, you pick up, centered at the first point, at this terminal point, and with radius r. So basically we want to say it is inside a closed disk. Once it is inside the closed disk, then the integral of f, let's call it gamma j, sigma j, let's call it sigma j. integral of analytic function over this closed curve is equal to 0. The integral of analytic function over this closed curve is equal to 0. So this implies the integral along the arc plus integral along the segment is equal to 0. Okay, go forward and backward. And when we move this to the other side, we get a negative sign. Negative sign means we can switch the order. When I say switch order, means you switch the initial and terminal point. Okay, so what does this mean? This means the integral of f along the arc is equal to the integral of f along the segment. So you have integral along the arc, 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 along the arc. It is equal to the integral along the segment. Okay, so we have that the integral of f along this initial curve is equal to the integral f along the z10, z20, zn0, and z10. Okay, so we use polygon to replace this. We use polygon to replace this initial closed rectifiable curve. We don't want to use a closed rectifiable curve because the initial and the terminal side are okay, but the middle step we cannot get the rectifiable condition. Okay, so we use this polygon. Okay, so this is the first. The first level is the replacement of the original curve by the polygon, and actually similarly for the terminal side, you see here for the terminal side you can also use this polygon to substitute the initial curve. So similarly, the integral over the terminal side, terminal closed rectifiable curve is also equal to the integral over the z1n, z2n, znn, z1n. Closed means that you start from the point, you go back to the point. Okay, so we have floor and the roof prepared. Now let's jump from one level to another level. Okay, so we'll fix each window. There are several windows together. This direction. Okay, so how do we get it? Well, first we know that each window, remember that we have this picture. Each window is contained in the one open disk. Remember we mentioned that. Where? Here, yes. Each window is containing an open disk. So each polygon, it is contained in the open disk centered at ZJK with radius r. If it is contained in this disk, of course it's contained in G. So basically we want it to be contained in G. If it is contained in the disk in the G, then in the disk is the essential. Then the integral of f over this polygon is equal to 0. Over this polygon is equal to 0. So assume here is the orientation. And be careful about this part. We actually use the reverse orientation. We use the reverse orientation. So if we move this term to the other side, we will get the integral of f here, jk, j plus 1k is equal to, you go backward, but when you move to the other side, you change the orientation. So it's a zjk plus 1, zj plus 1k plus 1. This is the bottom and the top part, and there are two sides, up and down two sides. Okay. We want to kill them, but they cannot be cancelled from one stuff. They will be cancelled if you consider them as a chain. You check here, this segment, if we consider this left window, the segment is upward. But if we consider this right window, the segment becomes downward. Okay, so here you consider one is upward, here you consider one is downward. They have different direction, and the value will have a different sign. Okay, so that's